Welcome, investigators. Step inside, close the door behind you, and let's get completely dialed in. You are looking at one of the most highly sensitive dossiers on our desk right now, the Cambridge AS and A-Level Mathematics 9709 syllabus. Today, we are opening a specialized case file focused entirely on 019 differentiation. Specifically, we are going to forensically deconstruct the gradient as a limit, alongside the precise mechanics of first and second derivatives. I am your lead detective for this session. I treat these Cambridge past papers exactly like intricate, high-stakes crime scenes full of hidden forensic clues, and you need to start treating them the same way. The historical evidence on our board shows that differentiation is one of the most fundamentally misunderstood areas in the entire mathematics syllabus. Why? Because candidates treat it like a simple smash and grab. They memorize the raw formulas, they drop them onto the paper, and they run away without ever grasping the underlying geometry or the examiner's true motive. Today, we are going to fix that. We are going to show you exactly what to look for when you dust your exam paper for mathematical prints, and how to build a case so bulletproof the examiner has no choice but to award you full marks.
Here is our investigative blueprint for today's briefing. We'll start in the evidence room, move through our forensic methodology, observe a tactical peer debate, pause for a mid-case briefing, conduct a live interactive audit, and finally get to case closed. Let's move. Section 1. The evidence room. Core principles and connections. To crack any case, you have to understand the core motive. Why do derivatives actually exist in this syllabus? I want you to mentally picture a curve on a graph. If you pick any two random points on that curve and draw a straight line, a chord, between them, you calculate an average rate of change. Basic algebra, right? But here is where the calculus fingerprint comes in. Imagine that second point sliding closer and closer to the first point along the curve. As the distance between those 2 points approaches absolute zero, that chord transforms. It becomes a perfectly balanced tangent line, touching the curve at one single microscopic coordinate. That beautiful concept, the gradient of a chord as its interval approaches zero, is the definitive foundational truth of differentiation. And as this direct quote from the official Cambridge Principal Examiner report proves, understanding this is non-negotiable. Examiners explicitly note that candidates who reference cross-topic connections achieve significantly higher marks. What does that mean for you? It means if you can seamlessly connect this raw limit of a gradient to finding the exact equation of a normal line in coordinate geometry, you instantly demonstrate to the examiner that you possess a high-tier conceptual understanding of the mechanics. You aren't just reciting a formula, you are proving the geometry.
Now look at this evidence table. This maps out the exact assessment objectives that examiners use to judge your paper. Notice how the expectations scale drastically as you move down the board. At the very top, we have level 1 knowledge. This is your basic descriptive domain. This is simply knowing the power rule, knowing that to find dy by dx, you multiply by the power and decrease the power by 1. It gets you in the door, but it doesn't close the case. To escalate to level 2 application, you have to actually use that first derivative to analyze relationships. This means taking your dy by dx, actively setting it to 0, and solving for x to locate a critical stationary point on the curve. But the ultimate goal, the place where the elite grade boundaries are decided, is level 3 evaluation. These higher order objectives demand that you interrogate that stationary point. You have to run it through the second derivative test, finding d2y by dx squared. You must provide a rigorously justified conclusion on whether that specific point is a maximum or a minimum, entirely based on whether your final evaluation yields a negative or a positive result. If you stop at level 1 or 2, you are leaving the most valuable marks on the table.
Section 2. Forensic methodology. The method mark strategy.
Let's step into the exact procedural framework you need to process complex differentiation problems without contaminating the scene. Listen closely. Examiners don't just care about catching the culprit, which is your final numerical answer. They care deeply about your verifiable paper trail. We call this the method mark strategy. Step 1. Extract from texts or tables. When you hit a massive wall of text in an optimization question, you must carefully isolate the physical constraints and set up your variables. You might need to define the volume of a cylinder using a single variable by substituting a given surface area constraint. Step 2. Interpret relationships. This is where you differentiate your carefully constructed equation. You find dy by dx, and you set it to 0 to locate those critical stationary points. Step 3. Draw evidence-based conclusions. This is the lock-in. You must conclusively prove the nature of that point using a valid mathematical test. This systematic 3-step analysis leaves absolutely no room for doubt. The beauty of the method mark strategy is that if your forensic procedure is completely documented and logically sound, you secure almost all the points, even if a tiny careless arithmetic slip happens along the way. Process is everything.
Section 3. The peer debate. Textbook versus logic string.
To truly understand how this works in the interrogation room, let's observe a hypothetical peer debate between two of our junior investigators, Agent Alex and Agent Sam. They are working on the exact same high-tariff optimization question, but their approaches are completely different. Look at the side-by-side comparison on our evidence board. On the left side, we have Agent Alex. Alex is a procedural detective who gathers mountains of raw facts, but fails to build a coherent case motive. Alex writes, "To find the maximum, you differentiate and set to 0, then do it again to see if it is negative." Okay, let's pause. That generic, descriptive block completely ignores proper mathematical notation. It lacks context. It's a raw textbook dump. It's like walking into court and just shouting the definition of a crime without linking it to the suspect. Now, shift your focus to the right side of the board. Here is Agent Sam. Sam builds tight, analytical logic strings. Sam writes, "By taking the first derivative of the given volume function with respect to the radius r, setting dv by dr to 0 yields a critical value of r equals 4. Substituting this into the second derivative, d2v by dr squared, produces a negative value of negative 12.5, confirming the stationary point is a strict maximum under the physical constraints of this specific model." Boom! Look at the difference. Sam uses a highly specific, context-linked evaluative response. Sam anchors the math directly to the variables of the case. Alex's generic answer instantly acts like a fingerprint mismatch. The examiner knows Alex doesn't truly grasp the application. Sam, on the other hand, secures every single available mark by locking the theory to the specific scenario. This is exactly how you need to structure your final paragraphs.
Section 4. Mid-case briefing. Top examiner warnings.
Case file, freeze, stop the tape. Before we reveal the final structural framework that will help you clear your upcoming Cambridge sessions, we need to make sure your intelligence feed is fully secure. Take a single second right now to subscribe to Ace the Exams at the handle @AceTheExams. Make sure you turn on all notifications so you literally never miss our weekly forensic exam updates. Whether you are cracking cases at IGCSE, O-levels, or navigating the deep waters of AS and A-levels, we are here to supply you with elite-grade masterclasses. Okay, back to the briefing. While we are paused, I want to run a vital mental check on mathematical constraints. When you are 20 minutes deep into a complex optimization problem, your logic cannot collapse under cross-examination. Always pause and verify your initial constraints. Did you isolate the correct variable? Did you double-check your initial algebraic equation before you recklessly applied the power rule? Ensuring your foundational equation is flawless is the absolute only way to prevent your entire chain of evidence from unraveling later on. Let's keep moving through the dossier. I want to rapidly fire through the top 3 fatal mistakes straight from the principal examiner reports. These are the repeat offenses that cost candidates an A-star every single year. Number 1, proper formatting omitted. Students constantly forget to write dy by dx equals or f prime of x equals. They essentially present a string of floating, disconnected algebra that miraculously turns into a derivative midway down the page. Examiners hate this. It breaks the chain of custody. Number 2, presentation conventions ignored. The syllabus demands proper headings and clear annotation. If you perform the second derivative test, but you don't explicitly write down d2y by dx squared to annotate what you are doing, the examiner cannot confidently award you those method marks. You have to tell them what test you are running. Number 3, answers lacking specific context. We just saw this with Agent Alex. Every single evaluation must be explicitly linked to the physical scenario given in the paper. If the question is about maximizing the area of a sheet pen, your final sentence better mention area, not just some abstract y value.
Section 5. The interactive viewer evidence room. This is where I hand the investigation files over to you. Put your detective hat on, because I'm putting you under the pressure of the clock. Imagine you have a 60-second countdown ticking away on your screen right now. You flip open a past paper and you are hit with a massive, multi-part optimization problem involving the curved surface area of a complex 3D shape. Your challenge is the visual clues scan. Before you write a single number, you must instantly extract the core trend from the text block. You have to ask yourself 3 rapid-fire questions. 1, what is the fixed constant they gave me? 2, what is the single variable I am going to differentiate with respect to? And 3, where is the hidden constraint equation linking my 2 variables, like radius and height? This high-speed visual clues scan, mapping out the architecture of the problem before you engage, is exactly what prevents you from chasing dead leads and bleeding precious time off the clock. All right, let's move to challenge number 2. Identify the counterfeit answer. Look closely at this highly flawed, medium-tier student response pinned to our board right now. It reads, "The gradient is found using the formula, therefore this is the maximum." I want you to locate the exact sentence where false logic and unverified assumptions completely destroy the overall mark integrity of this answer. Did you catch the discrepancy? It's right there in the second half. Therefore, this is the maximum. That is a completely counterfeit, unverified assumption. They successfully found the first derivative and set it to 0, sure, but they entirely skipped the forensic confirmation step. How do they know it's a maximum? It could be a minimum. It could be a point of inflection. You cannot just guess. You must evaluate the second derivative or utilize a first derivative sign test to conclusively, mathematically prove the nature of that stationary point. Descriptive fluff and counterfeit logic like this will instantly cost you all of your final accuracy marks. Section 6, Case Closed. Let's do the final investigation recap. Excellent forensic work today, team. Let's compile our final, high-scoring protocols to ensure you achieve that 100% case resolution score on exam day. To guarantee success in every single differentiation question you face, you must always follow these 3 chronological rules. Phase 1, decoding. Always execute a 3-step question scan. Extract the hard data, identify the specific variables you need to differentiate, and mentally map out your logic string before your pen touches the paper. Phase 2, timing. Utilize strict clock budget allocation. High-tariff evaluative questions require significantly more time because you have to justify your assumptions. Do not rush the algebra on the second derivative calculation. That is where the careless errors happen. Phase 3, review. Conduct a final evidence audit before you turn the page. Check your mathematical formatting. Are your annotations perfectly clear? Did you define your derivatives properly? And most importantly, did you answer the specific contextual question being asked? As we seal this case file and turn off the lights in the evidence room, I want you to leave today's explainer asking yourself this one final, absolutely crucial question every single time you sit down to practice. Are you just finding the derivative, or are you mathematically proving the method? Remember, the elite A-star marks do not go to the candidates who just memorize the power rule. The marks go to the investigators who prove their case mathematically, logically, and beyond a shadow of a doubt. Keep your logic tight, stay highly analytical, and always remember to respect the limit of the gradient. Before you go, drop a comment below telling me exactly which Cambridge subject and level you're preparing to conquer next, and make sure you hit subscribe at Ace the Exams for more weekly masterclasses. I will see you in our next explainer. Case closed.